Hi everyone, I am the Thai. This week, let's study about basic digital system design. We will study from today, Monday to Friday in the morning. And on Friday afternoon, we have 2-hour examination. Okay. For this course, we study about computational logic circuit, sequential logic circuit. For sequential logic circuit, we will study synchronous and asynchronous finite state machine. And the reference textbook is this one and this one. Okay, at first, for digital system, okay, the signal or variable in the system can have only two values, okay, namely maybe 0 or 1 or low and high or something like that. For example, let's consider this one. For example, this point maybe 0, 1, 2, 3, 4, 4.5 volt. This point may be 4.4 volt. For example, in analog circuit, 4.5 and 4.4 is different, but in digital it's the same. It's high, right? Logic high. So in digital system, we will consider the voltage from 2 to 5 as logic high, and voltage level from 0 to 0.8 as logic low, and between this is invalid. Okay. The advantage of digital system, the first one is noise tolerance, namely, for example, if the transmitter send the signal maybe at 5 volt and leave the receiver with some noise disturb, the voltage may be dropped to 4.5 volt. Okay, in analog it's different or have some error about 0.5 volt, but in digital system 5 volt is logic high, 4.5 also logic high, so there is no any error in digital system, so it's good, okay, for noise tolerance and easy to design because the system involve only 0 and 1 value for each variable in the system, and for digital system is programmable, high flexibility, small size, but various function, so on. For digital system implementation, okay, we must consider cost. Okay, cost means size, space, and power. Okay, to minimize it. And there are two types of digital circuit. The first one is combinational logic circuit. The second one is sequential logic circuit. For combinational logic circuit, for example, this one, if I apply input 1, 1, 0, the output may be 1, 1. Okay, and if I apply the value of 0, 0, 0, output may be 0, 1, and if I apply the input value 1, 1, 0 again, the output will be 1, 1, namely the same input value with give the same output. Okay, this kind of circuit is called combinational logic circuit. And the output depends on only its current input. Okay, to implement this one, we just connect logic gate, okay, without any feedback. Namely, we use feed forward connection. By the way, for the sequential logic circuit, okay, the output not depend only on input value. For example, if you apply 1, 1, 0 as the input, output may be 1, 1, and then when you apply 0, 0, 0, output may be 0, 1. If you apply 1, 1, 0 again, the output may be 1, 0. Okay, same input, but it may be get different output. Okay, the output based on the sequence of input. For example, remote control. Okay, for example, TV. Okay, television or remote control. When you press channel up, the channel will change from 1 to 2. Okay, when you press up again, it change 2 to 3. If you press up again, it change 3 to 4, and then if you press down, down, up, down, okay, the output will change to maybe 3, 2, 3, 2, for example. Okay, namely the output based on the sequence of input. So we call this kind of circuit as sequential logic circuit. Okay, to implement this one, okay, it has some feedback connection. For example, this logic gate connect to this one, and this one maybe some feedback. Okay, this output feedback to the previous input of the logic gate, something like that. And we use latch or flip-flop, okay, as memory, okay, of the circuit. And this one output depends on the sequence of input. It's time dependent, and it has state memory. Maybe use flip-flop or latch, okay, and state memory, okay, to keep the condition equivalent to the input sequence from the past to the current. And we will study and design two kinds of sequential logic circuit. The first one is synchronous circuit. The circuit will synchronize by clock, okay, global clock, and asynchronous, okay, we will operate without any clock. Okay, for logic gate, basic logic gate is AND gate. This one is AND gate. We will use this symbol, and we use dot or multiply as AND. Okay, the function will be 1 when these two input are 1, 1. Okay, if one of these is 0, output will be 0. And for OR, we use plus for OR. The two table for OR gate or OR function is this one. Namely, the output will be 0 if and only if both input is 0. But if some input is 1, output will be 1. Okay, next, inverter. Okay, the output will be opposite to input. Namely, when input is 0, output is 1. When input is 1, output will be 0. Okay. For the symbol, we use this triangle and circle at the output. Okay. Or in equation and expression, sometimes we use x prime, sometimes we use x bar. Okay. It means input. Okay. And NAND gate. For NAND gate, NAND is not AND. Okay. Not AND. An invert of AND. For AND, the output will be 0, 0, 0, 1. When you invert, it's 1, 1, 1, 0. So we use logic symbol is this one, and then inversion bubble at the output. Or NOR gate, not OR. Okay, not OR. So the output will opposite to OR. Namely, for OR, output will be 0, 1, 1, 1. For NOR, output is 1, 0, 0, 0. And exclusive OR. Exclusive OR, we use circuit symbol like this. And for the operator, we use plus sign and circle around the plus sign. For XOR function, the output will be 1 when input x and y is different value, namely 0, 1 or 1, 0. If the value of x, y are the same, the output will be 0. For XNOR, okay. XNOR, exclusive NOR, okay. Opposite to XOR, namely the output will be 1 when input are the same. If input is different, output will be 0. And buffer, this one, buffer. Output will be the same input. Okay. Now, let's consider CMOS circuit first. For CMOS, okay, CMOS is from two kinds of MOSFET, namely NMOS and PMOS. And the terminal of MOSFET basically have 3 terminals, namely gate, drain, and source. It's something like this. Maybe source of carrier, maybe electron or hole. It's like water in the tank. And then we have gate to control amount of water or amount of carrier, okay, to flow to the drain. Okay, source, gate, and drain. Okay, and okay, for the structure, it's based on the conductor material, namely at first for p-n junction, assume this side is p, this one is n. For forward bias, we apply external voltage source. Right? Positive polarity is at p material and minus at n material. In the configuration, the current will flow from p to n, and then the current will flow along in the circuit. But if we apply in reverse bias, Pn minus at here, plus at here, reverse bias, no current in the circuit. Okay, for N type semiconductor, the majority carries electron, namely there are amount of electron, okay, greater than number of hole. And for P material, the majority carries hole, namely number of hole is greater than number of electron in P. Okay, now let's consider this one first. Okay, for this MOSFET. MOSFET is from metal oxide semiconductor, namely at gate terminal. This one is metal, and this one is oxide, is insulator, and this one is semiconductor material. If I apply voltage source at here, what happened? This one is N material, this one is P. N, P, right, is positive at N, right? So it's reverse bias at this junction, so there's no current. Anyway, if I apply plus potential at gate, namely if I apply positive voltage at gate, in this point we have higher potential than this side. What happened? This positive potential will attract or pull the negative charge or electron, okay, from P material to gate. Anyway, because this oxide is insulator, that means electron cannot flow through this insulator, so it's stuck at here or accumulate at here. So what happened? Namely, when electron accumulate at here, then number of electron at here now become greater than number of hole. So now this area have the property like N-type semiconductor. That means now the current can flow from here to here. Okay, so this behavior is like switch. Let's switch. This point, maybe like drain and source, and the control is gate. Okay, when you apply nothing, it's like open circuit, namely the current cannot flow through this transistor. Anyway, if you apply positive voltage at here, it's like you turn on switch, namely you connect this point and this point together. So now the current can flow from drain to source. Okay. For this one, when you apply positive voltage at here, will pull electron which have negative charge accumulate at here, and then it make this area become negative channel, so it's called N channel. So we call this kind of transistor as NMOS. Now for this one, and the metal is PNP. Again, if I apply voltage like this one is positive This one is negative, P is positive, and maybe negative is maybe forward bias at here, but at this junction, this is minus, right? This is lower potential than this one, so it's reverse bias at this junction. Again, there's no current. Anyway, if I apply minus voltage at here, okay, compare with this one, then namely now gate has lower potential than this one. So what happened? The negative potential will pull or attract the positive charge or hold, okay, from this material to accumulate at here, and then it become positive channel or become P type material. So now the current can flow from P to P. Okay, this kind of transistor is called PMOS. So now if we bring NMOS and PMOS, okay, to make a circuit, then it's become CMOS. Namely, for example, if we connect PMOS at here and NMOS at here, what happened? If I apply 0 at here, this one is ground or 0 voltage, okay, ground. Okay. The 0, same potential, okay, transistor not turned on. 0 at here, 0 at here, positive at here. That means this point has lower potential than this one. So you attract the positive charge or hold accumulate at here. Then this transistor turn on. That means the current can flow from this one to this point, okay? Or the potential at this point and this point become the same, okay, like a switch, right? Switch. When you put switch, when you turn on switch, this point and this point, okay, will be the same voltage or same potential. So now V out become 5 volt. So when input is low, output will be high. And if I apply 5 volt at here, the one also 5 volt, same potential, nothing occur, okay? It as work as open circuit. 5 at here, 0 at here, so it's positive, right? This point is higher voltage than this one. That means you attract, okay, electron or negative charge accumulate at here, and then it become N channel. So now it's like switch turn on at here, namely this point and this point will be the same potential, namely the output now become 0 volt. Okay. Namely when you apply logic high, output V out become logic low. So the function of this circuit is inverter. Namely, when you apply low, output become high. When you apply high, output become low. Okay, this is inverter or not gate. For convenience, let I use symbol of time resistor like this. Namely, when you apply 0, this transistor is turned on. It's called active low. Active low. Okay. When you apply low at here, this bubble means low. Okay, low. When you apply logic low at here, this transistor will turn on. Turn on means this point and this point connect together with 0 ohm or very low resistance like switch that make this point become the same potential as this point. And by the way, for this transistor will be turned on when you apply logic high of 5 volt, for example. So this one is active high. Okay. Active high. So no circle at here at gate terminal. Okay. That means now if I apply 0, this is active low. That means when you apply low at here, this transistor will turn on. This point connect together. This one, no circle at gate, so it's active high. That means when you apply low or 0 at here, this transistor still be off. So output connect to this point, then become 5 volt. But if you apply 1 at here, this active low then not active or turn off. This one active high. That means this transistor turn on. This point and this point become the same potential. And because this point connect to ground, so it become 0 volt at the output. Okay, this is the inverter or NOT gate circuit by using CMOS. Note for connect PMOS and NMOS. Okay, for PMOS circuit must connect to the upper part that connect to 5 volt, and NMOS must be connected to the low part that connect to ground. You cannot swap this one and this one. Okay. Why? For example, if you use NMOS at the upper and PMOS at the lower part of the circuit, what happens? If you apply 5 volt, this one also 5 volt, then nothing occurs, right? If you apply 5, this one is ground. That means if you electron accumulate at here, that means this point still be N-type material. So this one is P, this one is P. So the current cannot flow through this one. Okay, because the junction should be one of these is reverse bias. And if you apply 0 at here, the ground or 0, nothing occur. It's off at here. It's 5 at here, but because 0 is lower than this point, that means okay, 0 is negative. Okay, it's negative when compared with 5 volt. That means the positive charge or hold will be accumulate, will be attract at here. Anyway, because it's positive, that means this area still be P-type material. So this N, this is P, this N. So one of these will be reverse bias. So there's no current. That means the transistor should be off. Cannot turn on. So you must connect PMOS circuit at the upper part and NMOS circuit at the lower part that connect to ground. Okay. Next example for this one. Now let's consider if I use active flow or PMOS. Okay, PMOS connect to at the upper part that controlled by input A and B. together in serial. And the oral part, okay, controlled by A at here and B at here. These two transistors Q1 and Q3 connect in parallel. So what happened? If you analyze circuit, for example, if you apply 0, 0, this one is on, this one is on, right? Active low, and this one active high, so this one is off, That means now the output will be connected to 5 volt or logic high, okay? But if you apply 0, 1, this is active low, right? That means this one on, active low, but you apply 1, so this one is off. 0 at here, this one is off because it's active high. 1 at here, this one is turned on. So now the output connect to ground, so it's become 0 at here. That means when you apply 0, 1, output will be 0. Okay, low, high, output become low. Okay, you can analyze something like this. And when you apply 1 at here, 0 at here, this one off, this one on, and on at here, and off at here. So now the output connect to ground, then it become 0. And the last one, when you apply 1, 1 at here, because this active low, that is off. This one active high, so it's on and on at here. So now the part that connect output to ground, so output becomes 0. Okay, where this path or this path. Okay, so this one, okay, we give the truth table function like this, or NOT gate. The next one, how about this? For this one, the upper part, okay, the gate controlled by input A, B connect in parallel, but the lower part connect in series. So analyze when you apply 0, 0 at here, this one is on, this one is on, output connect to VDD. So it becomes 5 volt or logic 1. When you apply 1 at here, 0 at here, this one is off, right? This one is on. Okay, this one on, but this one off. So now output connect to VDD, then it becomes 5 volt or logic high. And when you apply 0 at here, 1 at here, this one is on, this one is off. This one turn off, this one turn on. Again, output Z connect to VDD, then become logic high of 5 volt. And the last one, when you apply 1, 1 at here, this transistor off, this transistor off, this one on, this one on. So now output connect to ground become 0. Okay, output will be 0. Only one case when apply AB with 1, 1. So this function is NAND, right? NAND gate. Okay, you can analyze by in something like this. Anyway, if you, for this example, if you analyze by this method for 3 input, that means you must apply the input with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, and so on until 1, 1, 1. Okay, 8 possibility for the value A, B, C. It takes time, right, to analyze. So actually you can analyze by this method, namely, for example, this one. Let's consider when this output will connect to 5 volt or VDD. When, okay, the output will be high when this transistor and this transistor turns on, right? Then we turn on when A is low and B is low, okay, in series. Namely, it will be high when A is low, A is 0, and B is 0. So you can write A prime and B prime, okay, for output Z. Or you can consider the lower part of the circuit. If you consider the lower part of the circuit, if the lower part of circuit one of this transistor turn on, the output will be 0. So the question is, when output Z will be 0? When this one or this one turns on, right? So maybe because it's controlled by A and this one controlled by B, so you can write as A or B. Anyway, when you apply 1 this one turn on, this one turn on, A is 1, B is 1. The result of this expression is 1, right? But the circuit, when this one on or this one on, the output will connect to ground, output becomes 0. Okay, so you cannot write equation like this. You must invert it, right? Okay, invert this value. So now 1 invert becomes 0. That means if you apply the analysis at the lower part of the circuit, you must invert, right? Invert. Because when the lower part of the circuit turn on, the output will connect to ground. But equation give 1 as the result, so you need to invert. So if you consider upper part of the circuit, your result is Z equal to A prime and B prime. Okay, but if you consider lower part of the circuit, you get A or B and invert out. Okay, the same result. Okay, same result, namely A plus B prime equal to A prime and B prime. Okay, by De Morgan. Okay, or you can write two tables to compare. Okay, so for this one also you can analyze by this idea. But at first you must observe that if the upper part of the circuit connect in series, the lower part must be parallel. And for this one, upper part parallel and lower part is in series, connect in series. So you can write only upper part or lower part of the circuit. If you consider upper part of the circuit, that means now you consider when the output become 1, right? Or connect to VDD. So this one is parallel to this one, controlled by A, controlled by B. So this transistor will be on when A is 0. This one will be on when B is 0. So so you can write Z is 1 when A is 0 or B is 0. So you can write is A prime or B prime. This is the result of the analysis. Anyway, if you consider lower part of the circuit, you consider when Z connect to ground. When Q1 and Q3 turn on both, and because it's controlled by A and controlled by B, so you can write like this: A and B. Anyway, when you apply 1 at here, this one turn on is make output Z connect to ground or become 0. But this expression A and B, when A, B is 1, it gives 1 as a result, so you need to invert this term to make the output become 0. Okay, that means now for this one. Here this transistor connect in parallel, and this one in series. So you can, for example, analyze by only lower part of the circuit or upper part of the circuit. Let's consider this one at lower part of the circuit. Now our Z will connect to ground when A is 1 and B is 1 and C is 1. So A and B and C. Anyway, when you apply 1, 1, 1 at here, B and A and B and C give 1 as a result. So you need to invert this term to make the value become 0. Okay, like the circuit when this 3 resistor turns on. Okay, outputs connect to ground or become 0. Okay, that's all. So the function is A and B and C, and invert all of them, or 3 input NAND gate. Okay, and for this one, just show you, and this part is inverter. Okay, this part is inverter. So invert of invert, then it become buffer. Okay, the same value. And how about this one? For this circuit, for this one, this part. For this part, at this point, okay, you consider this point. This point we connect to ground when A is 1, B is 1. Okay, when A is 1 and B is 1, then it connect to ground. So this point is A and B prime. Anyway, this part of the circuit, this one, is inverter. So the output then become invert of this term. Then it become invert of A and B prime, so it become A and B, or AND gate. So note that in transistor level, AND gate, okay, is operate have longer propagation delay time. Now it take time longer than NAND gate. And the next, okay, let me analyze this circuit. Again, we can analyze just only upper part of the circuit or lower part of the circuit. Okay, why? Because if you consider this controlled by A, and this one controlled by B, and this one controlled by C, this controlled by D, this one controlled by C, D, B, and A. Note, for upper part of the circuit, Q2 and Q4 is controlled by A, controlled by B, connect in parallel. Okay, at lower part, A, B, connect in series, right? And CD at the upper part connect in parallel, but CD at the lower part connect in series. And this one series with this one, but this one parallel with this one. So if you see that the upper part and lower part are duality together, duality, that means if upper part is series, lower part is parallel. If upper part is parallel, lower part is series, something like that. Okay, so it's called duality. Okay, so you can use only upper part to analyze the function, or use only lower part to analyze the function. For example, if I consider lower part of the circuit, so it becomes what? B, right? This one is A, controlled by A. Let's read together, then become A and B, right? For this one, C and D. And because two of these parallel together, that means this term and this term are together. Okay, that when you apply an input value to turn this circuit or this circuit on, the output will connect to ground. Anyway, because when you apply 1 at here or 1 at here, it make this term become 1. But at the circuit output Z will connect to ground, so you need to invert this one. The result is AND and then all together and then invert. This kind of configuration is called AND or invert. Okay. For this one is all and invert, namely for this one A, B, A at here. This one controlled by C. So this one is A, this one is C, this one is D, this one controlled by B. And now note, and this transistor Q1, Q3 controlled by AB connect in parallel together. Okay, this one and this one parallel together, and this one parallel together, and this series together. So you can write expression as A or B. Okay, for this part, and this part C or D. Okay, and this part series with this part, so you use AND. Okay, and don't forget, because output Z will be 0 when this and this turn on, so you need to invert this term also, so that it become OR. Okay, OR, use OR gate, and then the output of OR gate AND together, and then invert, OR and invert, OR and invert. And now please note, okay, as I said, if the upper part of the circuit is controlled by the same input signal connect in series, okay, the lower part will be parallel, and if our part is parallel, our part must be series, something like this. And this one controlled by A, controlled by B, controlled by A, controlled by B. Okay, this one is parallel, this one is series. CD parallel at the upper part, controlled by CD transistor is in series connection in the lower part, and this one series together, this one parallel together, so it's duality. So the output is this point. Okay, this one also. Okay, AB series at the upper part, AB parallel at the lower part, CD connect in series at the upper part, and the lower part connect in parallel, and this group and this group parallel together, the lower part, this group series together, something like that. Okay, so we use this one, this 8, okay, for transistor. Okay, this one is used for this transistor, okay, and so on. Okay, now to design, that means to design. For example, if I start from A, okay, active high controlled by A, active low transistor controlled by A, and then if I add B parallel to A at the upper part, at the lower part must add B series to A, and we add C at here, okay, series to B, V we must add C parallel to B at low part, and D parallel to B, no, D C to B, and the last one E C to D, E parallel to D. Okay, and then you combine upper part and lower part of the circuit together, and this junction, okay, is the output of the circuit. Okay, now to design, for example, if you know the function right in this form, actually you can write, for example, lower part of the circuit. After that, you can find out the upper part of the circuit by consider this one. Namely, you just add a node or vertex, okay, in the loop of this one, and this one. After that, you connect by adding edge or line connect between this node and this node. The line that cut or intersect this line that controlled by A, that means this one controlled by A, also by active low. Then you connect this point and this point together, because this line, okay, intersect this line that controlled by B, that means this line must controlled by B bar, okay, controlled by B with active low, okay, and this one cut C, so this one C bar, and this one, okay, cut D, so this controlled by D bar, and this one cut E, that means this one controlled by E bar, and this point go to this point, okay, with infinite, okay. So this become this one. After that, when you connect this one to this one together, then it become this. So you bring the output from this point, then you will obtain the complete CMOS circuit. And don't forget that the low part of the circuit must be active high or NMOS. The upper part of the circuit must be active low transistor or PMOS. And the output is this point that connect between the connection between active low and active high of the circuit. And for this page, I show some parameter of the signal in the digital circuit. Namely, for the ideal case, any point of the circuit, the value of variable can change from 0 to 1 or 0 volt to 5 volt. But in practical, because of internal resistance and capacitance, okay, the signal cannot change suddenly, but it will change like this curve from high to low also. Okay, it cannot change from 5 to 0 suddenly, but it will decay slowly. So this parameter for rise time and fall time to represent how long that it change from logic 0 to 1 or logic 1 to 0. It's called transition time. You have to change from low to high or from high to low. Normally we use if we start from the lowest as 0 and highest as 100%. So we will measure rise time and fall time from 10% to 90%. point to this point. Okay, this one is rise time, and it go from 90% to 10%. It's called fall time. One more parameter is called propagation delay. Propagation delay means, for example, this one is circuit. Okay, this input, this one is output. If the input change, the output change, and then wait until see the change at the output. Okay, when input change, and then wait until can observe the change at the output. So the time that take when input change until output change by this input is called propagation delay. Like this. When input change and then wait until output change. Okay? This duration is called propagation delay. Okay? Namely, it's like to it's like how long the signal used to take from input to the output. Okay, the time that it take when input change until the output. Okay, show the change at the output terminal, like the signal travel from this point to this point. Okay, and for this one, let's consider this circuit. When enable is zero, what happened? This zero, this input, then it's come 1 at here, 0 at here, and this one is A at here, 0, and A is 0, and then input, then it become 1 at here, 1, or A is 1 input, then become 0 at here. Because this transistor is active low, so it's off at here. This one active high, so off at here. That means output not connect to VCC, not connect to ground. It's like open circuit, okay, or high resistance or high impedance, okay, like open circuit. Okay. But if I apply 1 at here, what happens? 1, then 0 at here, 1 at here. This one is A, and 1 is A, then this point is A invert. A or 0, then is A, this one also A invert, right? Okay, so if A is 0, what happened? This point is 1, this point is 1, so this one is turned on. Output become 0. Okay. But if A is 1, what happened? This point is 1, this point is 1, this one A invert, so it becomes 0 at here, 0 at here. Okay, A is 1, A invert becomes 0, A invert becomes 0. So this one is turned on, this one is off. That means now output connect to VCC or become high 5 volt. That means when input is 1, output is the same as A. Namely, it's buffer function. Okay, controlled by enable signal. If enable is 1, okay, the circuit acts as buffer. Namely, the value of A will go to the output. But when enable is 0, okay, output, this one is off, this one is off. Output become high impedance, like open circuit at this point. Okay, now this kind of logic is called three-state buffer. Namely, at the output can have logic low, logic high, and high impedance. Okay, the last example is transmission gate. For transmission gate, we use two sets of two transistor, NMOS and PMOS. For the control signal at gate terminal will be opposite. Okay, opposite. Namely, when this point is 0, this point must be 1. When this point is 1, this point must be 0. For example, if enable is 1 and here enable active flow enable, this point must be 0. So now this one is turned on, active low, right? Turn on. 1 at here, this one active high, so this one is turned on. That means now B and A connect together. That means the signal, okay, can transmit from A to B or B to A. Anyway, if I apply 0 at here and 1 at here, okay, opposite, this one is off, this one is off. So now B, okay, and A, these connect together, not connect together. So for example, for the application for transmission gate, consider this one. At first, for this part, this one is inverter, right? This point connect to VC and this one connect to ground. Namely, if S at here, this point will be S prime. Okay. If S is 0, namely this point will be 1. And 0 at here, 0 at here, 1 at here, 1 at here. Namely, when S is 0, this one is on, okay? This one is off. So output Z connect to input X for S is 0. But for S is 1, this point becomes 0, okay? 1 at here, 1 at here. And this one is off, on. So output Z connect to Y. Okay? So when for this example, when S is 0, output Z become X. When S is 1, output Z become Y. Actually, this circuit is multiplexer, okay, or mux. Okay, now let's talking about how to represent the logic circuit. Many methods to represent. For example, you can represent by writing or using some statement or description. For example, output F is 1 when Z is 1, only all both X and Y are 1. Something like that. Or you can represent the function by use mathematical expression like this, or draw circuit diagram, or using timing diagram, or use two tables, okay, to represent the function. Okay, now before go to detail how to represent the function, let's consider about this switching or Boolean algebra. This one, okay, Boolean or switching algebra. At first, for the variable or signal name, in mathematical expression, we treat it as variable, but in the circuit, maybe we consider it as the signal in the circuit. Anyway, it's the same, okay? Signal name or variable name, and operator, and or invert, okay? It's basic operator. Okay, for this one, just show the combination between variable and operator. Okay, and if you assign, okay, the value of this expression to maybe the output signal, maybe you use equal, okay, or use equation, okay, to express that this value, okay, assigned to this one. And axiom, okay, axiom minimal set of basic definition that assume to be true, okay, from some condition, okay, of the system, okay, need not to prove because it's true, okay, by definition. For example, axiom 1 said that if x is not 1, x is 0. If x is not 0, x is 1. Namely, and this assumes based on the fact that in digital circuit, okay, the value of variable or voltage level at any point in the circuit can be only low or high, or 0 or 1 only. Okay, it cannot be enter value. It cannot be 1 and 0 at the same time. Okay, it cannot be empty. Okay, it must be 0 or 1. For example, that for define not operation, namely when x is 0, x prime is 1. When x is 1, x prime is 0. And for exam 3, 4, 5, and just for define and operation and or operation. Namely, when input is 0, 0, the result is 0. 1, 1, 1, 1, result is 1. 0, 1 or 1, 0, output of n is 0. Similarly for OR gate also, okay, 1, 1 is 1, apply 1, 1, 1 at here, output is 1, 0, 0 at here, output is 0, 1, 0, output is 1, 0, 1, output is 1, okay. This is basic, okay, axiom. Now, for switching algebra, there are many theorems. Theorem means the statement that always true, okay, for every condition or every possible value of the input variable. For example, x or 0. This part is or, right? Or x plus 0 is x, right? Because when x, because it's digital system, the value of x can be 0 or 1, right? When x is 0, then it becomes 0 plus 0 equal to 0. Okay, 0 plus 0 equal to 0. It's true, right? Based on this axiom. 1. And when x is 1, when x is 1, so it's become 1 plus 1. 1 plus 0 is 1. 1 plus 0 is 1. This one. Okay? Axiom 5. So it's always true. So it's a theorem. You can prove, okay, by this technique. Okay, it's called perfect induction. By substitute all possible value of the input variable. Okay. And for this one, x and 1 is x. Okay, 1 plus any value is 1, 0 and any value is 0. The same value plus or add together will be the same value. Invert of invert, okay, become that value of variable, okay, opposite or complement, okay, plus together become 1, okay, because one of these must be 0. If this one is 0, this one is 1, okay. When plus together, the result is 1. If this one is 1, x prime then becomes 0, okay, add together then it becomes 1. And for the opposite value, add together become 0. Namely, if x is 0, x prime must be 1, add together is 0. Or this one is 1, x prime is 0, add together is 0. Okay, one of these must be 0. Then when add together, it give 0 as a result. Okay. And there will need list, okay, of theorem for switching algebra. For example, x plus y equal to y plus x, or x and y equal to y and x. Okay, it's commutative. Or you can do this one first, or do this one first. We give the same result. It's associative. Or this one, x and y, x and z. Okay, and it's the same, right? You can factoring, okay, x and then it becomes this one, x and then y plus z, this one. Or if you start from right hand side, you can distribute, okay, xn to y and xn to z, okay, x and y plus x and z, this one also, right? X or y and z, you can consider this one, okay, x or y and x or z. For this theorem, okay, if you connect the circuit based on this left hand side, sorry, you will use 2 AND gate and 1 OR gate, right? Something like this. Write this one, right? X and Y, X and Z, all together. Okay, so this function, okay, is X and Y or X and Z. Anyway, if you connect by using right hand side expression, you will use Y or Z and X, okay, fewer logic gate than this one, so you can reduce size or reduce cost of the circuit. Okay, theory number 9 also, if you connect the circuit based on this expression, you use 1 AND gate and 1 OR gate. Anyway, if you simplify or reduce the term, you need not to use any AND or OR gate. Okay, this one also. And for theory number 10, you use left hand side to make the circuit. You use 2 AND gate, 1 OR gate, and 1 inverter. Anyway, actually you can reduce to be x, that's safe number of logic gate. Okay, and this one also. Okay, this one you can reduce this term. This term you can remove it. still we keep the same result. This one also. Okay, just for example. To prove of this, we can use perfect induction, okay, by substitute all possible value, okay, of the variable. Namely, if you have two variables, you apply four possible values of x and y as 0, 0, 0, 1, 1, 0, and 1, 1. Okay, but for x, y, z, okay, you x, y, z, you apply 8, right? Possible value of three variables 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, and apply for left hand side and right hand side. Okay, its value are the same for every case of the input value. That means it's always 2. Page to show in variable theorem. For example, x plus x plus x plus x, okay, equal to x. X and x and x equal to x, okay, something like this. Okay, you can prove. How to prove? You can prove by using finite, okay, induction. Finite means number of terms. Number of x is finite number, okay, not infinite. Okay, to prove this, you normally we use 2 steps to prove. The first one is basis step. The second one is induction step. The idea is something like this. Okay, for the basis step, okay, we prove for smallest number of variable. For example, when n is 2, when n is 2, then it becomes x plus x equal to x. Okay, hope that is true. In this case, it's true, right? By this theorem, right? X plus x equal to x. And after that, for induction step, we prove that for n equal to I, we assume that it's true, and then when n equal to I plus 1, okay, should be true also. That means we assume when n is I true, we must prove that n is I plus 1 is true also. So something like this. Like this. The first step, you prove that when n is 2 is true. Okay, correct. And then for induction step, we assume that when n is I, assume that it's true. Assume that it's true. And then you prove that when this one, if this case true, the next, okay, when n is I plus 1, if you can prove that it's true also, that mean if this one true, the next one will be true also. When this one true, the next one is true also. When this one true, the next one is true also. That means it's true for every case. So it's called finite induction. For example, for basis step, n is true, then is x plus s is x. Okay, it's true according to theorem number 3. And then for n is I term, okay, if the one equal to x is true, then when n is I plus 1, that means I plus 1, that means it's one term plus I term. And based on this assumption, this I term equal to x. That means this I term, okay, equal to x. Then it becomes x plus x, okay, is equal to x also. So now you prove both induction step and basis step. That means this theorem is true. Okay. Okay. Now, for standard representation, in the basics representation is two table. This one. Namely, if you write down two table, input variable x, y, z, and do the sequence of binary counting, then it becomes 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on until 1, 1, 1. Okay. For the same function, we will give the same two table. Okay, that's all. So table is standard one. Okay, and another one is canonical form. Canonical form, maybe canonical sum or canonical product. Okay, to represent the function. Something like this. Okay. Now, example for this one is two table. Normally we use the sequence of binary counting order for the input, and then is the output of the function. And before go to the next topic, okay, let's review this terminology. Literal is variable or complement of variable, for example x or x prime, okay, for example. And product term is logic product, mean and, okay, and operator of two or more literal. For example, x and y, or x and y prime and z, something like that. Single literal also, okay, treat it as product term. For example, z or z prime, okay, product term, single literal. And sum of product is in logical sum in all, okay, of product term. Namely, is sum of many terms, and this term is in product or and, okay, between literal or variable. Okay, it's called sum of product. Like this example, sum term is single literal or logic sum of two or more literal. For example, this one, sum term, okay, this literal, sum together. If we bring, okay, this sum term and together, okay, then it become product of sum. Okay, product of sum. And for normal term, is product of sum term which have no variable appear more than once. Okay, for example, this xx, okay, appear two times, so it's not normal term. Okay, for normal term it must appear x only one time. This one also, w plus w, okay, you can write only w, okay, one times. Okay, now Okay, min term. What is it? Okay, min term mean is for minimum. Okay, min term. Okay, let's consider this one for min term. First of all, for 3 input. Okay, 3 input variable. There are 8, right? 8 possibility. Okay, 8 combination value for 3 variable. Minimal case that give logic 1 output of the term is called min term. So, what kind of function that give result only one case? It's similar to AND, right? AND operator. Namely, for example, if X and Y and Z, this term will be 1. This term will be 1, just only one case, right? When X is 1, Y is 1, Z is 1. Okay, minimal case that term will be 1. It's called min term. So it must be and, right? And together between all input variable. Must be all input variable. Why? For example, this point is very important. If your system have 3 input, for example, X, Y, Z. Okay. At first, if the function of this is f equal to x prime and y and z, this term will be only one case when x is 0, right? Y is 1, z is 1. Okay? Only one case. If you apply another value of x, y, z, for example, if you apply 0, 0, 0, this term will be 0, right? Okay. If you apply 0, 1, 0, 0, right? And then it becomes 0. Okay. It will be 0. It will be 0 for every case except the value 0, 1, 1. So this term give the result of only one case. It's called min term. Okay, now what about this function? First, more example. If I want x, y, z, the output become 1 when input is 0, 0, 1. What is the min term? Of course, it should be AND together, right? Between all input variable. It will be 1 when what? When all term, right, is 1. But when you apply 0, 0 for x and y, it's not 1, right? So you must invert it here, right? That means min term for this example is x prime and y prime and z. Okay. Okay, now what happened if your system have got 3 variable x, y, z, but your function is, for example, is x and y prime? What happened? This term will be 1 when what? When x is 1, right? When y is 0. Okay. When x is 1, when y is 0. So how many cases of the input that can make the output become 1? How many cases? 1 case? No. Don't forget that this system have 3 input, X, Y, and Z. Okay? When you apply input Z also must be applied by some value, maybe 0 or 1, right? So, because output Z must be 0 or 1, okay? Cannot be empty, right? So, it may be 1, 0, 0 for X, Y, Z, or 1, 0, 1. So, there are two, okay? Two input combination that can make output become 1. That means this term is not min term. It's not min term. It's not min term because min term must make the function become 1 only 1 case. But for this term, give 2 cases that make output become 1. Or if your function is x, only x, what happens? Function is 1 when x is 1, right? But if your system has 3 input variables, that means when x is 1, maybe 1, 0, 0, or 1, 0, 1, or 1, 1, 0, or 1, 1, 1. There are 4 cases. So, x is not min term. Okay. That means for min term must AND for of all input variable, right? And of all input variable. If some input variable is removed, okay, and the case that make number of the case that make a function become 1 will be increased. Okay, from for min term only 1 case. When you remove 1 variable, there are 2 cases. When you remove more 1 variable, it becomes 4. Okay, and so on. The value that make the min term become 1, okay, is called min term number. Okay, you can write it in binary form or decimal. And max term is maximum case, okay, but not all, right? Maximum, but not all that make the result of the function become 1. For example, if your system have 3 variable, for 3 input variable, there are 8, right? 8 case, okay, of the input combination. Okay, the maximum case, but not all. That means 7 case that give the output become 1, except only 1 case. It's not 1. I mean it's 0. Only 1 case. Okay, this term is called max term. What kind of function that give 0 only 1 case? Yes, all right. This term or this term or this term, okay, will be 0 only 1 case when the value of this term is 0. All. So for max term, for example, x, y, z output f. Your output f is x plus y prime plus z prime. This term will be 0 when what? When x is 0, right? When y is 0, right? When z is 0. No, sorry. When y is 1, when z is 1, right? Okay, 0 plus 1 prime becomes 0 right here, plus 1 prime becomes 0 right here. So then 0 or 0 also becomes 0. This one is max term. Okay, this term is max term because output become 0. That's only one case when x is 0, y is 1, z is 1. Again, if I remove one of these, for example, remove this term, so now your function become y prime plus z prime. Then it will be 0 when y is 1, z is 1, right? So y1, z is 1 will give output become 0. But your system have got 3 input variable. Input x must have the value 0 or 1, right? So there are 2 cases that make output become 0. So this term is not max term. It's not max term. Okay, because max term must give 0, only one case. But this one, 2 cases that can make output become 0. Or if I remove y prime, so the function just only z prime. That means this function will be 0 when z is 1, right? Z is 1. So there are 4 cases. 0, 0, 1, 0, 1, 1, what else? 1, 0, 1, and 1, 1, 1. Okay? Z is 1. These 4 cases can make function f become 0. So this term is not max term. Okay? This term is not max term. For max term, must be write in all operation between all input variable. And the value that can make, okay, the max term becomes 0, okay, it's called a max term number. Okay, you can write in binary or decimal. Okay, now if your function, for example, like this, f is 1, 1, 1, 1, 1, for input 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, and 1, 1, 1. Okay, when you apply this kind of input, will give output of the function become 1. But if you apply 0, 0, 1, output becomes 0, 0, 1, 0, output is 0, 1, 0, 1, output is 0. Okay, now if I want to make the function from this two table, what should I do? Okay, at first, let's consider each input that make output become 1. Namely, for this one, we want when input is 0, 0, 0, right? The corresponding minterm is x prime and y prime and z prime. For this one, okay, this term. For this one, the corresponding input 0, 1, 1. Its minterm is x prime, y, and z. This one, right? Will be one, only one case. Okay, when input is 0, 1, 1. And this one is 1, 0, 0 is x, y prime, z prime. This one only one case. And this one 1, 1, 0, okay, become 1 only when input is 1, 1, 0, or its minterm is x and y and z. This one, and this one is 1, 1, 1, x and y and z, right? So Now, if we write down all minterm that corresponding to logic 1 output of the function. So after that, you all add them together, all all or sum of this minterm together, you obtain the complete function, namely your function is this term plus this term plus this term plus this minterm plus this minterm. So if you apply the value of x, y, z with 0, 0, 0, this term becomes 1, this term becomes 0, right? This term becomes 0, this term becomes 0, this term becomes 0. When you add together, because this term is 1, then the result is 1. Okay, now if you apply this one, 0, 0, 1, this term becomes 0, 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 0, 0, 1, not corresponding to any minterm of the function. That means the minterm of the function will be 0 all. So when you all them together, the result is 0. So the input that make some minterm become 1, that also make the function is 1. That's all. This expression is called canonical sum. Sum of product, sum of minterm. Or you can write in short from sigma and write in binary value of x, y, z that can make output become 1. Or write in decimal form. Or write in this style also, small m, lowercase m, and it show the value of x, y, z in decimal that can make function become 1. This is called minterm list or onset. Similarly, if we consider 0, logic 0 as of the output, so we use max term. Namely, for this 0, it will be 0 when input is 0, 0, 1. So its max term is x plus y plus z prime, right? This one. 0 only one case. For this 0, 0, 1, 0, the max term is x plus y prime plus z. So only one case, x plus y prime plus z. And this 0 is 1, 0, 1 is x prime plus y plus z prime. 0 only one case for x prime plus y plus z prime. And then we bring this max term and together. So the input that make this max term is 0. When add together, this input also make function to be 0, right? Because 0 and anything give the result of 0. But if the input that corresponds to any max term, so max term become 1, 1, 1. When all is 1 and together, it gives 1 as the result. So if you consider logic 0 of the output, you just find out max term, okay, max term that corresponds to the input that make the function become 0, and then you add all of max term together. You will obtain the complete expression for the function. This expression is called canonical product, okay, product of max term. Okay, or you can write by this symbol, okay, pi, right? And binary or decimal value is max term is all offset, okay. Or you can write this form, okay, pi and capital M followed with decimal value of input combination that make the function become 0. So if you know the max term list or offset, and you know number of input variable of the function, so you can, if you know of set or max term list, that means you can know or can write down the min-term list. Namely, if input for 3 variable that make output become 0 is 1, 2, 5. For 3 variable, input is from 0 to 7, right? But 1 to 5 make result is 0. That means 0, 3, 4, 6, 7 make function become 1. Now, if you get, okay, two table of the function, now you can write an expression, okay, maybe in canonical sum or canonical product, okay, to represent the function. Anyway, if you make the circuit follow canonical sum or canonical product, of course it work, right? It gives the result as you want. Follow the truth table. Anyway, number of logic gate, number of variable, or size of the circuit is so big. So now, if we want to minimize size of the circuit, what should I do? Okay, you should do by apply some theorem. For example, maybe use combining theorem to minimize or reduce number of variable or size of the circuit. Namely, for combining theorem, say that for example, x and y plus x and y prime equal to what? Equal to x. X and okay. And you can factor this one, x and y plus y prime. Y plus y prime equal to 1, right? 1 and x. is x. So in general, this term and this term plus this rectangle term and triangle term prime, the result will be this term. Okay, it's the same part. It's opposite or different. Okay, you can reduce by remove this opposite or different part, and the result will already this the same part of these two terms. It's called combining theorem. For example, this one is same a b c. This one is y prime. The result will be a b c. Okay, the same term. Or this one also a plus b plus c plus y, a plus b plus c plus y prime. Okay, the result is the same term, same part. Now, if we can reduce or minimize number of terms and number of variable or literals, the result will be minimal sum or minimal product. For minimal sum is minimal sum of product, namely number of terms that sum together will be minimized, and number of literal or variable in each term is also minimized. Okay. It's called minimal sum. For minimal product also, it's form of product of sum. Number of terms that product together is minimum, and number of variable that sum together in each term is minimized also. So now we want to find out the minimal sum or minimal product. Anyway, for this course, okay, we will emphasize for minimal sum first. Namely, we will consider, okay, logic 1 output of the function. Now, to minimize, we use one tool of them is kernel map. Okay, let's introduce this one. At first, consider this. If we write down the function by consider logic 1 output, of course we can write minterm of this, right? Namely, this one is x prime and y prime and z. This one is x prime and y and z prime. This one is x and 101, right? Y prime and z. This one is 111 is x and y and z, right? And then sum these four terms together. Then you obtain canonical product, right? Then you can complete the function. Okay, it's work, but it uses a lot of logic gate. So now we want to minimize, okay, or simplify them. How? If we use combining theorem, what happens? For example, this term, okay, same, right? Y prime, y different. So you can combine these two terms together and give the result of x and z, right? Okay, x and z. So you can consider this one, right? The input value of x, y, z is 1, 0, 1, right? For this one is 1, 1, 1. Okay, your result is x and z. That means This term will be 1 when x is 1, z is 1. Okay, x is 1, z is 1, x is 1, z is 1. Okay, not depend on y. Okay, not depend on y. Okay, y can be 0, y can be 1. Okay, not affect the result. Okay, because the result based on x and z only. Okay, not depend on y. Okay, this is the meaning. So what else? This term also, this one, different, this one, 0, this one, 0, 0, 1, 1, 0, 1, okay, this term, and this term, y prime z, right? X prime x. So if we combine these two terms, we get y prime z. Namely, this term will be 1 when y is 0, z is 1. Okay, y is 0, z is 1. Okay, not depend on x. X is 0 or x is 1. Okay, not affect the result. Okay, the result is 1 because y is 0, z is 1. Okay, not depend on x, something like this. So you can reduce or you can combine these two terms by observe, right? What variable is different? Okay, what variable is different? X prime, for example. Actually, you can observe from the binary value of input. For example, this one, and this one, right? Different only 1 bit. Y is 0, Y is 1. That means it's not depend on Y. Depend on only what? Only X and Z. X and Z is 1, 1. So this two term is X and Z, right? Or if you consider this one and this one, the same, right? 0, 1, 0, 1 for Y, Z, but X is 0, X is 1 at here. So it's not depend on X. It depends on only value of Y and Z. When Y is 0, Z is 1. So you can write as Y prime and Z. Yes, okay. You can look from two tables and can combine this term and this term together. Okay, but it's not convenient. So we will arrange. Okay, we write the two table to the new one that make the result of the table so that the input that different only 1 bit will be adjacent together. For example, this one we can write something like this. Because of 3 input variables, so there are 8 cases. Okay, 8 possible values. Let me write, for example, x, y, z, right? The input value 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Okay, this is the number outside the table is input value, and inside the table I will write output, okay, of the function. Namely, this cell this cell correspond to the output when input is 0, 0, 0. Okay, 0, 0, 0. Okay, output is 0. So this one is 0. For this cell, x, y is 0, 1, z is 0. Namely, x, y, z is 0, 1, 0. So you find out 0, 1, 0. Okay, it's 1 at here. Okay, from this. For the cell 1, 1, 0. 1, 1, 0. Okay, so it's 0. And so on. Right? This kind of table is called canal map or K-map. Note, the input of two adjacent cells will be different only one bit. Namely, for the cell, input value x, y, z is 1, 1, 1, right? 1, 1, 1. For the cell, input is 1, 0, 1. Okay, 1, 0, 1. Okay, one bit different. Okay, one bit different. So this point and this point also, right? For this one is 1, 1, 0. 1, 1, 0. This cell is 1, 1, 1. Okay, different only one bit. So use the K-map. It's easy. Okay, it's very easy to find out which one is adjacent together or different one bit. Namely, for this one, input is 1, 1, 1, right? 1, 1, 1. This one input is 1, 0, 1. Okay, 1, 0, 1. So you can combine these two cells together. Okay, namely is x, right? And z. Okay, not depend on y. So you can combine together by using this one. Okay. How about this? This term, its input is 0, 0, 1. Okay. 0, 0, 1. This term is 1, 0, 1. 1, 0, 1. Okay. Different one bit. Namely value of x in this case different. But for y and z it's the same. Okay, y is 0, z is 1. So you can combine these two terms together and give the result of y prime z. Okay, this cell, okay, most left and most right of the table, different one bit. You can look in as an adjacent cell. Okay, logically, okay, different only one bit. So you can combine them together. So to complete the function, you must select all cells that contain logic 1 output. Okay, and to minimize, you must use number of product term as small as possible. Namely, if you use this one, the product term of this one is x, y, z, right? Namely, only if you select only one cell, you obtain min term that appear all input variable. But if you select two cells, you will get what? In this case, x is 1, right? Y is 1, 0, so y disappear. This cell z is 1, this cell z is 1 also, so it becomes x and z. No, you reduce number of variable. If you select more small cell, okay, to group together. And this term also, then you get what? X is 0, x is 1, so x disappear. The product term, y is 0, so y prime, and z is 1, z. Your function is complete. You must select all logic 1 output or one cell. For this one, the corresponding input is 0, 1, 0, so it's x prime, y, and z prime. Now your function can make by sum of these three terms, namely this one. Okay, sum together, and then you can implement the circuit for this expression. Note, this term x and z will be 1 when x is 1, z is 1. Two cases. Y prime z will be 1 when y is 0, z is 1. Okay, two cases. Another case is 0. For x prime y z prime, we want only one case when x y z is 0, 1, 0 is 1. So when you add or sum them together, okay, the result will be 1 when one of these product term is 1, right? 1 add anything is 1. If the input, okay, not make any product term become 1, namely 0, 0, or when you add together, the result is 0. Okay. Another example for this one, when you write it out, KMap will give something like this. Now, to obtain the function by using sum of product, that means we must select, okay, all of logic 1 output. Anyway, to minimize, you must select bigger rectangular group of the one cell. Namely, you select this one, it's okay, but not say, okay. To reduce cost, you must select bigger size of the rectangular group. Okay. So if you select these two cells, the cell input x is 1, 1, so x, and y 1 at here, 0 at here, y disappear, z is 0, so x and z prime. And this one, this 4 cell, you can group together. Then it's become what? X is 0, x is 1, different, so x disappear, y is 0, y is 0. Out of this 4 cell, y is 0, so y prime. That's all. That means your function now you can write as x and z prime plus y prime. Okay. Okay. And note, for y prime, the result will be 1 when y is 0. Okay, y is 0. It's 1. 4 case. Namely the value, okay, not depending on the value of x and z. Namely, x and z can be when x and z is 0, 0, 0, 1, 1, 0, and 1, 1. Okay? Not affect the value of y prime. Right? And for x and z prime, this term will be 1 when input is x is 1, z is 0. X is 1, z x is 1, z is 0. X is 1, z is 0. Not depend on y. When you add together, okay, the input that make this term or this term become 1 will give the final result of the function is 1 also. Note that this cell you select or covered by this term y prime and also this term. That means when you apply what this cell is 1, 0, 0, 1, 0, 0. This input make both term, this term and this term, okay, become 1. Anyway, when you sum together, it also give logic 1 as the result. Okay, that's okay. Okay. Now, take a note that, for example, if we write K-map for 4 variable like this, for example, A, B, C, D, input is 0, 0, 0, 1, 1, 1, 1, 0. Be careful about the sequence of this, right? Must be different 1 bit, okay, or in gray code. 0, 0, 0, 1, 1, 1, 1, 0. If as you write the term of A and B and C prime and D prime, okay, can you write in this K-map? This term will be 1 when A is 1, B is 1, Z is 0, D is 0, right? So the cell is 1, 1, 0, 0, this one, okay, this cell. Okay, how about this term? A and B and C prime. Now I remove one variable. What happened? This term will be 1 when AB is 1, 1 and Z is 0, right? AB is 1, 1, 1, 1 and here, right? And Z is 0 here and here, okay? So let's cover this two cell for this term. Now if I remove more one variable, for example, I remove A, then it become BC prime. This term will be 1. This term will be 1 when B is 1, Z is 0. B is 1 at here and here, right? Z is 0 at here. So it's this 4 cell. Okay, it's covered this 4 cell for this term. Okay, and if I remove one more, I remove C prime, then this term B. This term B will be 1 when B is 1, right? So it covers this 8 cell. Okay? This 8 cell. Okay. So note that if you remove one variable, the size of group will be bigger and bigger, okay, from 1 cell to 2 to 4 and to 8, okay, depending on number of variables that we removed. So if you want to minimize the function, that means you should select the rectangular group or one cell as big as possible. That means must cover only one cell, but not cover zero or but not cover zero cell. And now, if some technical term that you should know. Now minimal sum you know already, right? Is sum of product expression. For the function that have fewer product term and fewer literal. In each term. Now imply. You should know imply. What does it mean? For every input combination x1 to xn such that p x1 to xn is 1, then function f is 1, namely the input combination that make product term p become 1. This input also make this function become 1 also. So it's called p is implicant of f or p imply f. For example, this one is product term p. This is f. Input 1 0 0 make p become 1. This input also make f is 1. This input 1 1 0 make p is 1. This input also make function become 1. So we said that p imply f. P is implicant of f. For prime implicant of the function is a normal product term p that imply f, so that if any variable is removed from p, then the resulting product term does not imply f. For example, this one. If assume if I start from this one, this term is 1 0 0, namely x y prime z prime. If I remove one variable, so it's maybe linked to this one. For this one is x is 0 is 1, y is 0, x y prime. X y prime mean is will be 1 when x is 1, y is 0. Anyway, if I remove what? I remove x. So it will cover this 4 cell, right? Y prime. Something like this. Now if you remove y, now it's become 1 1 1 1. It's not okay, right? Because this cell must be 0, this cell must be 0, this cell must be 0. If you remove it, you will cover all of this. That cover 0 cell. That's not okay. Namely, the product term of the biggest rectangular group of one cell is called prime implicant. If you remove it, remove more variable. For example, this one, this cell. For example, this cell is 110 x, y, z prime, right? If you remove y, so it covers these two cells. But if you remove x, for example, so now it's cover this 0 cell also. That means it's not independent. So the biggest, okay, the biggest one is this one. So the product term of this biggest group, okay, that contain only one cell is called prime independent. Okay, so for kernel map or K-map, okay, of initial function, prime independent, okay, is the product term of the biggest one cell group, okay, that cover only one cell but not cover any 0 cell. Okay, the next term cover. Cover is collection or set, okay, of implicant that account for all variations for which a given function is equal to 1. Okay. It's called cover of that function. And for example, set of all minterm, okay, is cover because all minterm that make function is 1, right? Or sum of all prime implicant also cover. Okay. Okay. This is called complete sum. If you sum all prime implicant, if you sum all minterm, you obtain canonical sum. And prime implicant theorem for minimal sum, okay, it's always a sum of prime implicant. Okay. And distinguish one cell or essential vertex. What is it? And essential prime implicant, okay, or EPI. What is it? Okay. Consider this example. For this example, to obtain the function, at first we must select all these one cell, right? And because this one cell is covered by only this prime implicant, that means to complete the function, we must use this term, right? This prime implicant. That means this prime implicant is essential, right? It's essential one. It's essential prime implicant. This cell is called distinct one cell. Distinct one cell or essential vertex. Okay, it's just definition that you should know. For the example, this cell is distinguished one cell because it covers only one prime implicant. This one also. So to complete the function, if we want to find out minimal sum, of course you must select this one. This one is essential prime implicant. You must cover all one cell. That means you must select this one also. It's essential prime implicant. Okay, this one also. That's all. and cost. What's it for cost? The definition, okay? Number of gate plus total number of input of all to all gate in the circuit. And the primary input, namely literal, okay, for both uncomplement and complement input variable. Okay, I assume that it have zero cost. Namely, for example, for this function, x1 bar x2. This one is literal, this one is literal, right? You can treat that zero cost, okay? And together, x3 and x4 bar, x3 and x4 bar, and these two terms all together. Okay, to count cost, number of gate, how many gate? 1, 2, 3, right? Plus total number of input to all gate in the circuit. 1, 2, 3, 4, 5, 6. 6 input, right? When you plus sum together, then it becomes 9. Okay. And this example is x1, x2, x2 bar and together, or x3 and then invert, right? x4 bar plus 5, x4 bar or x5, and this one. So let's count the cost. There are 1, 2, 3, 4, 5 logic gate, right? And number of input is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 input, 5 logic gate. Then the cost is 14. For this one, let's show example that some function, okay, may have no any essential prime implicant, and some function may have more than one minimal sum. For example, this one. For this one, there is no any discrete one cell, right? Because one cell cover with more than one prime implicant. So there is no essential prime implicant. And to find out minimal sum, maybe this one, or use this one. So there are two sets, okay, of minimal sum. Okay, this is just summaries. Okay, for this example, if you want to find minimal product, okay, you can use K-map to find out it, similar to a minimal sum, but for minimal product, you just focus on logic 0 output of the function. So you write down at here, and then you can select something like this. Okay, it's two cell will be 0 when input x is 0, y is 1, right? So the sum term is x plus y prime, right? Because this term will be 0 when x is 0, y is 1. Okay, x is 0, y is 1. And this term will be 0 when x, y, z is 1, 0, 1. So you can write as x prime plus y plus z prime. So your function in mineral product, you just sum this, you just AND, okay, these two terms together. Okay, that's all. Namely, the input, okay, that make this term become 0 will also make the function become 0, because 0 and anything become 0. And this page said about don't care. Don't care some circuit, okay, some input combination, okay, we don't care, okay, we can ignore the output. Namely, for example, is some circuit and your input may be from 0 to 9, okay, or in binary 0000 to 1001, okay, and this circuit will show the result, something maybe connect to 7-segment display to show the result as 1 or 2 or 3, something like that. So because your input we apply to this circuit is 0 to 9 or 00 to 1001, that means for input 1010 until 1111, okay, do not apply to this circuit. So that means you can ignore the output of this input. Okay, it's called don't care. Don't care. What happens if your function have don't care? For example, for onset, namely if your input value is 1, 2, 3, 5, 7, your function must be 1. But for don't care set is 10 to 15. The output may be 0 or 1. Okay, 0 or 1 is okay, both. And if your input is what? 0, 4, 6, 8, 9. Okay, not in on set, not in don't care set, the output of function must be 0. Okay, so in case of don't care, to minimize the function by using command, you can do by this process. At first, we must select all logic 1 output, all 1 cell. You must choose all of this. To minimize, you may use don't care or not used. If you use it, that means you treat it as logic 1 output. If you don't use it, that means you treat it as 0. But at the first step, you don't know you will use or not. Okay, so you can write it 0 or 1 at the same time, or write D in the cell. Okay, now if I select this 4 cell, this 4 cell is N3 to N1, N0 is 0, 0, 0, and N3 prime, N2 is 0 at here, 1 at here, so N2 is absent in the term, N1, 0, 1, okay, absent, N0 is 1, and N0. And for this, 1, right? And to minimize, you should not select only this one cell, but you should select these 2. Anyway, if you include these 2 cells, namely now if you treat this don't care cell as 1, you can obtain bigger size of rectangular group. Namely, now include is cover this 4 cell, so it's become what? N3 0 at here, 1 at here, N3 absent, N2 0, 0, okay, N2 prime, and N1. That's all. So the new function is this product term plus this product term, like this. Okay. And note that when you obtain this function will make the selected cell to be 1 as the result, and the cell that not used, the result will be 0. Okay.